Good morning, students. In the previous class, we have seen the introduction part of oxidation states, that is generalization. What are the general oxidation states of D block elements? And from top to bottom in D block elements, according to P block, like that it won't be happen. So what will be happen here? Top to bottom, stability of higher oxygen state increases. But in P block, because of inert pair effect, stability of lower oxygen state increases from top to bottom. But here, from top to bottom, stability of higher oxygen state, stability increases. Okay, that one we have discussed in the previous class. Now our next side reading is, let us start with 8.3.5. Trends in the M+2 such that M standard electrode potentials. This is our next side reading. Before going to this one, generally we will take any metal in neutral state, that is metal atoms, that is metal M. Okay. What is the general characteristic of metal? Losing of electrons or gaining of electrons? It is losing of electrons. Generally, metals want to lose the electrons. So, let us consider this metal. If this metal loses the electron, it will be converted to M+2. Okay, this process is called oxidation. Now we are going to see trends in the M+2 such that M standard electrode potentials, meaning when a metal is converted from metal state to M+2, what about their electrode potentials values? How they are going to be varied in D block elements? That one we are going to discuss. So when a metal M is going to be converted to M+2, plus 2 electrons, which process is going to be taken place? Oxidation is going to be taken place. Okay. At the same time, here in electrochemistry we have discussed that already. Metals with low reduction potential value will undergo oxidation easily, and metals with high reduction potential values will undergo reduction easily. We will depend on only reduction potential values. Okay, if you remember these 2 points keenly, we can go through the explanation easily related to trends in the M+2 such that M standard electrode potentials. Is it okay? One more time. Metals with low reduction potential values will undergo oxidation easily, and metals with high reduction potential values will undergo reduction easily. So according to the reduction potential values, we can discuss that one metal will undergo reduction easily and one metal will undergo oxidation easily. In what way their values are going to be varied practically, all those things we want to discuss now. Okay, that one in the form of a graph they gave. Let us see that graph. Titanium, first series. Titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, these red dots are observed values, normal theoretical values. Green dots are calculated values. For titanium, both observed value and calculated value is exactly same. Vanadium, chromium, manganese also, iron. For all these elements, titanium, vanadium, chromium, manganese, iron, calculated value and observed value both are same only. But for cobalt only slightly difference, nickel also, zinc, almost copper is also getting similar only, copper and zinc also. But see here, this is 0 on y-axis. Lower than 0, these are all negative values. So titanium, vanadium, chromium, manganese, iron, cobalt, nickel, zinc, all metals are showing negative values except copper. Copper is the only element metal which is showing positive value in this series. Are you observing now? These are all negative values. Only copper is showing positive value in this series. And one more thing, this type of tabular column is very important. There is a chance to be asked in direct theoretical question, normal subjective question, or sometimes case-based questions also there is a chance to be asked. So be careful and understand the things clearly. Let us the things, what are the things they gave. Table 8.4 contains the thermochemical parameters related to the transformation of the solid metal atoms. See, related to the transformation of the solid metal atoms to M+2 ions in solution and their standard electrode potential values. That only I told, metal is converted to M+2 ions. How much easily metal is going to be converted to M+2. To understand that, if M is going to be converted to M+2, it is undergoing oxidation. So, if a metal wants to be converted to M+2, it should undergo oxidation. It should contain lower reduction potential value. Okay? See, the observed values of E0 and those calculated using the data of table 8.4 are compared in figure 8.4. Okay. The unique behavior of copper having a positive E0 value. The unique behavior of copper having a positive E0 accounts for its inability to liberate hydrogen from acids. This one, according to our reactivity series also, we might have seen that copper cannot liberate hydrogen from its acids, H2SO4, HNO3 like that. Copper cannot liberate. Okay, so it is less reactive, meaning it cannot lose the electrons easily when compared to other metals. That's why it has higher. If it is not able to lose the electrons, then it is ready to undergo reduction. If it is not ready to undergo oxidation, definitely it is ready to undergo reduction. Reduction means it has higher reduction potential value. Okay, see, accounts for its inability to liberate. By seeing this positive E0 value, it is accounted. Why it is getting positive E0 value? Because it is not able to liberate hydrogen from acids. Only oxidizing acids, nitric acid and hard concentrated sulfuric acid, react with copper, but they also will not liberate hydrogen gas. They will liberate nitrogen dioxide or nitrogen oxides like that, but they won't liberate hydrogen. Nitric and hard concentrated sulfuric acid react with copper. Okay. The acids being reduced. The high energy to transform copper to Cu+2. The high energy to transform copper to Cu+2 is not balanced by its hydration enthalpy. Let us consider copper. Copper must be converted to Cu+2. In previous class, we have seen the ionization enthalpies. Okay, ma? For the conversion of copper to Cu+2, (745 plus 1958) total 2703 kilojoules per mole of energy should be required. It is very high amount of energy. Okay, we are giving that much amount of energy to convert that copper to Cu plus 2. Actually, Cu plus 2 is nothing but simply it won't be converted, it must be present in aqueous solution. Okay, now one more important definition we want to see now. From here onwards we will use regularly, so concentrate highly. When Cu plus 2 is dissolved in water, immediately that Cu plus 2 is surrounded by water molecules. Not only that, generally any salt, if it is dissolved in water, that salt contains positive and negative ions. They are going to be surrounded by water molecules. Copper contains which charge? Positive charge. So oxygen partial negative charge. It is nearby, pointing hydrogen outwards, like this. This Cu plus 2 is going to be surrounded by water molecules. There is an attraction between opposite charges, partial negative charge of oxygen and Cu plus 2. Because of that, some amount of energy will be released. That amount of energy released when that ion is surrounded by water molecules is called hydration energy. When that ion is surrounded by water molecules, at that time amount of energy will be released, which is called as hydration energy. Hydration is the term related to water. The energy released when the ion is surrounded by water molecules. Is called hydration energy. So here they are giving explanation in a way that the high energy to transform copper to Cu plus 2, one small thing, I added only ionization energy 1 and ionization energy 2 only, but here enthalpy of atomization also must be added, because solid state must be converted to Cu plus 2. In previous class we have seen already, when a solid state metal is converted to Cu, any metal dipositive ion, 3 energies must be we have to supply. 3 energies must be supplied. Those are enthalpy of atomization, first ionization enthalpy, second ionization enthalpy. These 3 energies must be supplied to convert a metal to dipositive ion. This is very high amount of energy required to convert copper to Cu plus 2. It is not balanced by its hydration enthalpy. The general trend towards less negative E0 values across the series is related to the general increase in the sum of the The general trend towards less negative E0 values across the series is related to the general increase in the sum of the first and second ionization enthalpies. Here, this conversion of metal to metal plus 2 ions is highly related to E0 values, as well as that E0 value is depending on this first and second ionization enthalpies. Now only we told high amount of energy is required to convert this copper to Cu plus 2. Okay, ma? So the general trend towards less negative meaning they will undergo somewhat reduction easily only. Okay, that is because across the series is related to the general increase in the sum of the first and second ionization enthalpies. See, when there is increase in the sum of the first and second ionization enthalpies, high amount of energies are required to convert those metals to M plus 2 ions. Then they are not able to be converted from metal to metal plus 2 easily. That means they will not undergo oxidation. See, I am writing here. Metal to metal plus 2 ions require, general trend left to right, increase. We observe there is a increase in sum of IE1 and IE2. When there is an increase in sum of IE1 and IE2, high amount of energy is required to remove the electrons from metal to convert that metal to M plus 2. That means it is slightly difficult. So this process, when we go through the general trend, this process is getting difficult. Conversion of metal to metal plus 2, because there is an increase in sum of IE1 plus IE2. I hope you are understanding, ma? Okay. It is difficult to convert that metal to metal plus 2 because there is an increase in sum of IE1 plus IE2. Then oxidation will not be taken place easily. Instead of that, they will undergo reduction somewhat easily. Not that much also, reduction. This is leading to less negative values. If it is high negative value, the value is very less, then they will undergo oxidation easily. Correct? That is the meaning. Related to D block elements only we are talking now. See, observe the point once again. The general trend towards the less negative E0 value is nothing but somewhat reduction will be taken place easily when compared to oxidation. Across the series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of E0 for manganese, nickel and zinc are more negative than expected from the trend. See, this is the expected value, this is the calculated value. For cobalt, this is the observed value, this is the calculated value, highly negative. When compared to our observed value, calculated value is observed value is almost minus 0.5 above here. This value is minus 0.5 below, meaning this is higher negative value. Nickel also showing higher negative value. Zinc also slightly showing higher negative value. Okay. Finally, I will give one conclusion. When there is high reduction potential value when compared to other metals, it will undergo reduction easily. When there is low reduction potential value when compared to other metals, it will undergo oxidation easily. Those points we want to remember highly. Is it okay, ma? Now, this study is clear. I hope you understood. Why they have less negative E0 values across the series is related to the general increase in the sum of the first and second ionization enthalpies. Okay. Now we will see one tabular column and how we are going to explain. Let us see that one. Thermochemical data for the first row transition elements and the standard electrode potentials for the reduction of M plus 2 to M. Okay, this is related to reduction potential values. Okay, observe. Titanium. This is delta HA, that is enthalpy of atomization. This is 1, ionization energy 1. This is ionization energy 2. This is hydration enthalpy. Okay, E0 of V, E0 in volts minus 1.63. Minus 1.63. Okay, here easily we can explain how about these values. One or two values I will explain, and remaining we will just see that one. Now observe here. For titanium, titanium should be converted to Ti plus 2 in aqueous solution. What are the energies they are going to be involved? Energy absorbed and energy released. Titanium, when it is converting from titanium to Ti plus 2, two energies are involved. Energy absorbed, energy released. What are the energies absorbed? First one, delta HA, enthalpy of atomization. Second one, delta H1, delta HI. I is nothing but ionization enthalpy. Delta HA, enthalpy of atomization. This is first ionization enthalpy. This is second ionization enthalpy. These are the three energies which are going to be absorbed. And only one energy is going to be released, that is hydration enthalpy. Okay. Now what is the enthalpy of atomization for titanium? That is 469. First ionization enthalpy 661. Second ionization enthalpy 1310. This much amount of energy is going to be absorbed. 1310, 661, 469. Double 440 amount of energy is absorbed. Now what is the hydration energy? 1866 kilojoules per mole. Everything it is in kilojoules per mole. This much amount of energy is released. 2440 amount of energy is absorbed. Here 1866 amount of energy is released. Okay. So what is the net amount of energy? 2440 1866 574 kilojoules per mole amount of energy will be absorbed. So from this, what is the conclusion we will get? To convert titanium to Ti plus 2, this total net amount of energy is 570 kilojoules per mole, 574 kilojoules per mole will be absorbed. Okay, when there is high amount of energy required to convert that metal to M plus 2, that process will not be taken place easily. When there is high amount of energy required to convert that metal to metal plus 2, it will not be taken place easily. But here we have considered for only titanium first. Now we will go through by comparison one more metal we will take. Is it okay, ma? For comparison one more metal we will take and we will see what about that metal also. That one, vanadium, I will consider. I hope you are understanding. When a titanium is going to be converted to Ti plus 2, two energies are involved, energy absorbed and energy released. Total amount of energy absorbed, enthalpy of atomization, first ionization enthalpy, second ionization enthalpy. Energy released, hydration enthalpy. Hydration energy value is 1866. Total amount of energy absorbed is this one. So net amount of energy 574. E0 value of titanium is equal to minus 1.63 volts. Keep it in mind, this one also. Okay. Now let us consider what about vanadium. See, vanadium is going to be converted to V plus 2. At the time also same, energy absorbed and energy released. Here directly I am writing previously I wrote clearly what are the three energies absorbed: enthalpy of atomization, first ionization enthalpy, second ionization enthalpy. Now enthalpy of atomization for vanadium is 515. First ionization enthalpy of vanadium is 648. Second ionization enthalpy of vanadium is 1370. Add these three. (2533) kilojoules per mole amount of energy is absorbed. Now energy released is hydration enthalpy. What is the hydration enthalpy of vanadium? 1895 kilojoules per mole. In textbook they mentioned negative. Negative meaning is nothing but energy released. Negative meaning is nothing but energy released. That one only I am representing with arrow marks. Okay. This much amount of energy is released and this much amount of energy is absorbed. So what is the net amount of energy? 25331895. (638) kilojoules per mole amount of energy will be absorbed. Now let us compare titanium and vanadium. Before going to that one, vanadium E0 value. E0 value of vanadium is minus 1.18 volts. E0 value of titanium is minus 1.63 volts. Okay, now first let us compare titanium and vanadium. How much amount of energy is required to convert titanium to Ti plus 2? 574. How much amount of energy is required to convert vanadium to V plus 2? 638. Which one requires more amount of energy? Vanadium. Conversion of vanadium to V plus 2 requires more amount of energy. So conversion of vanadium to V plus 2 is not easy. Which one requires more amount of energy? That process will not be easy because we have to supply amount of energy from outside. Is it okay? When less amount of energy is required, automatically the process will be taken place easily. Now V to V plus 2 conversion is not easy when compared to titanium to Ti plus 2. Okay, V to V plus 2 process is called oxidation. So vanadium cannot undergo oxidation easily when compared to titanium. This is the conclusion. Vanadium to V plus 2 is not easy. That means vanadium to V plus 2 process is nothing but oxidation. Vanadium to V plus 2 is undergoing oxidation. Actually, it is not an easy process when compared to titanium. So I am writing now clearly. I hope you are understanding, everyone. Once again, titanium to Ti plus 2 conversion is required with 574 kilojoules per mole amount of energy. Vanadium to V plus 2 conversion requires 638 kilojoules per mole of amount of energy. The process which requires high amount of energy will not be taken place easily. So vanadium to V plus 2 conversion requires 638. That process will not be taken place easily. So vanadium cannot undergo oxidation easily when compared to titanium. Vanadium cannot undergo oxidation easily when compared to titanium, meaning vanadium will undergo reduction when compared to titanium. Correct? According to our electrochemistry, which one will undergo reduction? Which one has higher reduction potential value? So vanadium conversion E0 value is equal to minus 1.18 volts. Titanium conversion E0 value is equal to minus 1.63 volts. Minus 1.18 minus 1.63. Which is lower value? This is lower value. When compared to vanadium and titanium, E0 value is lower of this one. Now this is higher. The value which has higher value, reduction potential value, it will undergo reduction. See, vanadium will undergo reduction when compared to titanium. See, easily we got the point. By seeing this atomization, enthalpy of atomization, ionization energy 1, ionization energy 2. These three energies will be absorbed. Hydration energy will be released. Net amount of energy by seeing that one. If net amount of energy is greater, the process will not be taken place easily. Is it okay, ma? Like this we can compare. Actually, in the tabular column, for understanding purpose, I explained with the help of two metals, titanium and vanadium. Like that we can compare with any other and we can understand easily how these E0 values are related to enthalpy of atomization, first ionization energy and second ionization energy. I hope you are clear, ma. Just once I will explain and I will recall once. After that we will move to next concept. See, titanium is converted to Ti plus 2. That process is losing of electrons, oxidation. Correct? Energy absorbed. How much amount of energy? Enthalpy of atomization, first ionization energy, second ionization energy. This total amount of energy is absorbed. 2440. Energy released. That is hydration enthalpy. 1866 amount of energy. Net amount of energy 574. You will get positive sign only because 2440 positive, 1866 negative, because it is energy released. This is energy absorbed. Net amount of energy plus 574, meaning will be absorbed. 574 kilojoules per mole amount of energy will be absorbed. In the same way, I have seen for vanadium conversion also. In vanadium conversion, I got plus 638 amount of energy will be absorbed. From this, what we can conclude, the process which is required with high amount of energy cannot be taken place easily. So, vanadium to V plus 2 is not easy when compared to titanium to Ti plus 2. That means vanadium will not undergo oxidation easily. Then it should undergo reduction easily. By using E0 values also, we got the same conclusion only. See, titanium and vanadium, which has higher value? Vanadium, it will undergo reduction easily. Titanium, lower value, it will undergo oxidation easily when compared to these two metals. Is it okay, ma'am? Like that, if you see the other metals also, in this tabular column, they gave titanium to zinc, every enthalpy of atomization value, first ionization enthalpy, second ionization enthalpy, even hydration enthalpy. See, everywhere hydration enthalpy values are negative values only, meaning at the time of that positive ion is surrounded by water molecules, energy will be released only. That's why they gave the negative hydration enthalpy. These three are every time positive. See the net amount of energy for every metal and according to the E naught values whether they are undergoing oxidation or reduction. By comparison only we can tell. Without comparison it is not possible. So if you want to compare copper and zinc, first add these three values and this value must be subtracted. Net result, check that one. Then what about the copper? It got positive value with respect to zinc. Then whether it is undergoing oxidation or reduction we can say easily. Like this tabular column is helpful to us. The stability of the half-filled D subshell in Mn plus 2 and the completely filled D10 configuration in Zn plus 2 are related to their E naught values, where E naught for nickel is related to the highest negative hydration enthalpy. So some factors, depending on domination of some factors, we are going to explain the E naught values also easily. See, in this way we can explain what about the trends of D block elements coming to M plus 2 to M electrode potential values. Okay, negative value. Copper, among all these metals, copper has positive value. So when compared to any other metal, copper undergoes reduction easily because it has higher reduction potential value. According to energy also we can see. Okay, remaining ones you can try by comparison. Any doubts are there, I will clarify. This is about trends in M such that M plus 2. Conversion of metal to M plus 2. Okay, now coming to next 8.3.6. Trends in the M plus 3 to M plus 2. That means previously we have converted metal to M plus 2. Now we want to see M plus 2 to M plus 3. Its conversion depends on third ionization potential value, because amount of energy required to remove the electron from one electron from dipositive ion is called third ionization potential, IE3. Here this is depending on IE3. Okay, see, an examination of the E naught M plus is such that M plus 2 values shows the varying trends. The low value for scandium reflects the stability of Sc plus 3. The low value for scandium reflects the stability of Sc plus 3, which has a noble gas configuration. Okay, see, Sc plus 2 to Sc plus 3. Sc plus 2 configuration is argon. Normally scandium is scandium argon 4s2 3d1, right? Sc plus 2 means 2 electrons are lost from 4s. Then argon 3d1. Sc plus 2 configuration is argon 3d1. Sc plus 3 configuration is argon. Conversion of 3d1, this is unstable. This is highly stable. Conversion of this Sc plus 2 to Sc plus 3, it will be taken place very easily. It will be taken place very easily. This is which process? Sc plus 2 to Sc plus 3, it should lose electron. Means oxidation. So Sc plus 2 will undergo oxidation easily. This is according to electronic configuration we confirmed. See, Sc plus 2 has 3d1 unstable configuration, argon 3d1. Sc plus 3 has argon stable configuration. So the process, by losing one electron, it will be getting stability. So easily the process will be taken place, right? Correct. Then Sc plus 2 will undergo oxidation easily. If it undergoes oxidation easily, it has lower reduction potential value. Now observe the see. That one, it will undergo oxidation easily, meaning it has lower reduction potential value. That only. The low value for scandium reflects the stability of Sc plus 3, which has a noble gas configuration. The highest value for zinc is due to the removal of an electron from the stable D10 configuration of Zn plus 2. Okay, now coming to zinc, let us see. Zn plus 2 configuration is argon 3d10. Actually Zn plus 3 is not at all possible. Let us see. Zn plus 3 configuration is argon 3d9. 3d10 completely filled, which is highly stable. This is unstable. No one wants to lose their stability. So conversion of stable to unstable, it won't be taken place. So this process cannot take place easily. Which process this one? Oxidation. Zn plus 2 to Zn plus 3 cannot take place easily. That means oxidation will not be taken place easily. If oxidation is not taken place easily, it will undergo reduction. It will undergo reduction. When it is undergoing a reduction, then it has higher reduction potential value. When it is undergoing reduction, then it has higher reduction potential value. That only they gave here. Highest value for zinc is due to the removal of an electron from the stable D10 configuration of Zn plus 2. The comparatively high value for manganese shows that Mn plus 2. So if they have stable configuration, they will be containing high values, E0 values. Is particularly stable, whereas comparatively low value for Fe shows the extra stability of Fe plus 3 D5. The comparatively low value for vanadium is related to the stability of V plus 2 half-filled T2G level unit 9. Just 1 second ma, see here. Whereas comparatively low value for iron shows the extra stability of Fe plus 3, not Fe plus 2. See here. Conversion of Fe plus 2 to Fe plus 3. Ma, if you get any doubt like this itself, you can check. Now I explained for scandium and zinc na, like that for Fe plus 2 to Fe plus 3 also you can check. See. Fe plus 2 to Fe plus 3. Fe plus 2 configuration is argon 3d6, argon 3d5. This is stable, half-filled configuration. This is unstable. So the process easy. Conversion of unstable to stable easy. This is which process? Oxidation. If it undergoes oxidation easily, then it has lower reduction potential value. If it undergoes oxidation easily, Fe plus 2 to Fe plus 3, it has lower reduction potential value. That only they give. See. Whereas comparatively low value of iron shows the extra stability of Fe plus 3. Same, comparatively low value for vanadium is related to the stability of V plus 2 half-filled T2G level unit 9. Is it okay? That is about trends in M plus 2 such that M plus 2 standard electrode potentials. Next, trends in stability of higher oxygen states. Table 8.5. This one. Table 8.5 shows the stable halides of the 3D series of transition metals. The highest oxidation numbers are achieved in titanium X4 tetrahalides, VF5 and CrF6. The +7 state for manganese is not represented in simple halides but MnO3F. Highest oxidation state of manganese is +7 that is not MnF7, it is in the form of MnO3F is known. Okay, and beyond Mn no metal has a trihalide except FeX3. After manganese no metal has trihalide except FeCl3, FeX3, okay, and COF3. The ability of fluorine to stabilize the highest oxygen state is due to either higher lattice energy as in the case of COF3 or higher bond enthalpy. Higher lattice energy as in the case of COF3 or higher bond enthalpy terms for the higher covalent compounds. Generally, if any compound is existed in the form of covalent, highly covalent, means high oxidation number. Any metal, note down this one also, any metal which has highly covalent nature contains high oxidation number. Any metal which has highly covalent nature contains high oxidation number. Generally they will exhibit high oxidation number. Okay, any metal which has highly covalent nature, high oxidation number. Low covalent nature, low oxidation number. See, like that. The higher covalent bonds, example VF5 and CrF6, they will be existed in higher oxidation number when they are highly covalent in nature. Although V5 is represented only by VF5, the other halides, however, undergo hydrolysis to give oxohalides, VOX3. In this form, these are called oxohalides. Another feature of fluorides is their instability in the low oxidation states, example VX2. They are less stable in their lower oxidation states. Generally, this type of things will be happen when X is chlorine, bromine or iodine. Another feature of fluorides is their instability in the low oxidation states, example VX2. X is equal to Cl chlorine or Cl bromine or iodine. Okay, see, these are the formulae of halides of 3D metals. Titanium can show TiX2, TiX3, TiX4, +2, +3, +4. Vanadium can show these type of halides up to VF5, highest oxidation number +5. Chromium, CrF6 up to. Manganese is not able to form MnF6 or MnF7 because of high repulsions between the fluorine atoms. Somewhat chromium is bigger than manganese, so when it is bigger it can accommodate fluorines, number of fluorines, but manganese is not possible. That's why manganese with highest oxidation number is observed in MnO3F. In this, oxidation number of manganese is +7. Next, iron will show two types of halides, FeX2, FeX3. Cobalt, COX2, COF3. Nickel, copper, zinc. These are the formulae of halides of first series of D block elements. Okay, this is about today's class. I hope you are clear, everyone. Clearly, this tabular column is also explained to you. Please understand, don't feel any difficulty here. By comparing these energies, we can understand that which one is undergoing reduction and which one is undergoing oxidation. According to that, we can understand this E0 values. But basic things you have to remember that substance, metal with higher reduction potential value will undergo reduction easily. Metal with lower reduction potential value will undergo oxidation easily. Those things you have to remember carefully and you have to understand. So in this today's class, we have seen that trends in electrode potential values for m plus 2 such that m, and conversion of m plus 2 to m plus 3 also, and even trends in stability of higher oxidation states we have seen. In the next class we will continue this small concept in oxidation states and even chemical reactivity and E0 values also. After that, remaining concepts are very easy concepts, easily we can complete. Magnetic properties, colored complexes, all these things. Okay, ma? That is about today's class. I hope everyone you are clear what are the things we completed today. Everything it is neatly written on the paper, so make a notes neatly and follow the things carefully. Thank you all. Have a nice day.